Welcome to today's deep dive. We're going to do something totally wild today. Imagine this, no complex circuit diagrams, absolutely zero Verilog code. By just reading a simple JSON file, we are going to understand how to build a robust, space-grade 4K touchscreen chip. Sounds completely impossible, right?
So how do we actually pull this off? Well, we have to completely ditch the traditional coding mindset. We need to put on a new hat, a pure physical intuition hat. In the world of CSDL, we aren't talking about logic gates anymore, we are talking about actual physics.
Here is our game plan. We'll start by looking at JSON as hardware DNA, then explore the chip's muscle, system adaptation, conservation and time, analog and digital division, and wrap up with those core physical intuitions. Let's get right into it.
All right, Section 1, JSON as hardware DNA. This is a massive paradigm shift, guys. Normally, you probably think of JSON as just static software configuration data. But in CSDL, it's a completely different beast. It is the physical initial condition. Change a key value pair here, and you are literally altering the physical constitution of the analog chip. It's living hardware DNA.
Moving on to Section 2, let's talk about the chip's muscle, specifically the alpha stiffness gain. When we crack open this space-grade HMI JSON file, the very first thing we see is the number 6.55. Now, this isn't just a random value, it's the pixel drive strength. It gives the transistors the physical push they need to drive liquid crystals perfectly, even if the temperature swings from a freezing -40 to a blazing 85 degrees Celsius.
Alongside that 6.55, we have a touch sensitivity gain of 8.21, which amplifies even the tiniest 0.1 picofarad finger movements. And the best part? These numbers weren't painstakingly hand-calculated by an engineer. The CSDL engine evolved them naturally to find the absolute perfect Pareto optimal balance for noise resistance, power, and performance.
On to Section 3. Let's look at how the system adapts to its environment through epsilon strain sensitivity.
Here, we see a value of negative 0.025. What does that mean? Well, a negative value means that when the screen gets physically pressed, it actively lowers the equivalent capacitance. It's basically a genius active defense mechanism that compresses the signal to prevent false triggers.
So the screen essentially yields first and then stabilizes. We see the same gentle adjustment with ambient light at negative 0.008, so the screen doesn't flicker wildly. And because it's direct drive, that mechanical strain turns straight into an electrical response. No continuous, power-hungry ADC sampling required.
Section 4, Conservation and Time. This is where the math really bridges into the physical hardware.
In this blueprint, there's a specific number strictly locked in at 14.0. We call this the magic hypercube constraint, or simply M.
Think of M equals 14.0 as our anchor. It absolutely guarantees global pixel charge conservation. This means, for a 14-bit panel, the total brightness error stays under 0.1%. Your screen is never going to get weirdly bright or dark in one spot, because the total charge is fiercely protected.
And what about time? Well, the baseline relaxation time, or tau, is normally 8 picoseconds. But the second you touch the screen, tau jumps to 22 picoseconds. The system purposefully slows down, adding physical inertia to act as an analog filter. It literally wipes out your finger's natural jitter, and it does this with zero CPU overhead. How cool is that?
Section 5, Analog and Digital Division. This right here is the ultimate chiplet layout.
The division of labor is just brilliant. The 60 Hz refresh rate is driven by an analog oscillator, making it completely immune to space radiation. Touch and display actually share the same OTA computing unit by mapping sensitivity to physical strain. And the digital side? It uses a cheap, older 13-nanometer process purely for protocol translation. It does absolutely no computing. The analog physics does all the heavy lifting.
Finally, Section 6, Core Physical Intuitions. Let's wrap this up with the 4 vital questions you need to ask.
You might want to take a screenshot of this one. When you see alpha, ask, how hard is it? For epsilon, how does it adapt? For tau, how fast or slow must it react? And for constraint M, what total amount is being protected? Master these 4 questions, and you have completely mastered CSDL hardware mapping.
As the quote says, do not view JSON as a software configuration. View it as a living, breathing, physical system. So after seeing how elegantly we can control the physical world, Are you ready to stop writing code and start orchestrating physics in your next hardware design? Thanks for joining me on today's deep dive.